in order to solve a practical fluid system, our previous internal energy equation is not yet sufficient. We need an equation of state. And so to see how this works in practice, we're going to consider the simple condition of an ideal gas. And for an ideal gas, we have our equation of state that P is equal to rho times R times T. And we also know that the internal energy E is equal to the specific heat at constant volume times the temperature. And this specific heat at constant volume, this is specific heat. This is a way of converting from temperatures to energies. And for an ideal gas, this has the value R over gamma minus 1. And so the internal energy is R times temperature divided by gamma minus 1. As you might notice, in ideal gases, the thing that enters our equations a lot is the combination RT. That shows up in the momentum equation, and it's showing up here as a pair. You get the R and the T together consistently in the equations. All right, so if we now introduce these into our internal energy equation, we start with our Lagrangian form of the internal energy equation, dE by dt, and we'll use the full form for now with non-adiabatic effects. So this was T ds dt minus P over rho div u. This was our general form. And now we'll specialize to an ideal gas by putting in our equations for E and for P over rho. So E, this becomes, assuming a constant gamma and a constant gas constant, we get a R times gamma minus 1 out front times dt, and this is equal to T ds dt, and then minus P, that's rho over rho RT, itself divided by rho, and so that just becomes RT times the divergence of U. All right, so if we now clean things up by dividing things across, we get that dt is equal to gamma minus 1 over R T ds dt minus just T minus the R's canceled, but the gamma minus 1 is still here. So minus gamma minus 1 T div U. This term here, right, this is 1 over CV, and CVs come together with entropies to convert entropy units into a non-dimensional number. CV is the ergs per Kelvin, energy per temperature. That happens to be the unit of specific entropy as well. So we might actually write this further as dt is equal to T times the quantity ds over CV, assuming no changes in R or gamma here, dt minus now gamma minus 1 T div U. This is dimensionless. As is gamma, meaning that all or the S over CV is dimensionless. So this has units of 1 over time, and all of the terms in the equation have units of temperature per time, our d by dt and our T div U. All right. Now for adiabatic motions, we have the entropy does not change with the motions. And in that special circumstance, for an adiabatic ideal gas, we obtain that dt is equal to minus gamma minus 1 t div u. This is for an ideal gas with adiabatic motions. And otherwise, we've just used the first and second law of thermodynamics to get ourselves here. As we had seen when we introduced the temperature equation without motivation, the temperature in a Lagrangian sense can change from compression of the fluid by squeezing or expanding the fluid. If we squeeze the fluid, if div u is less than 0, then the temperature goes up when we squeeze it. And if div u is greater than 0, then the temperature goes down as we expand the gas. Now, for an ideal gas, under adiabatic conditions, we can rewrite our temperature equation as a pressure equation instead. So we can write, we can do a transformation of variables to pressure. So sometimes, also, you'll see that as dp dt equals minus gamma, just one gamma, times p div u. And the difference between gamma minus 1 or gamma comes about from the density factor in the continuity equation in converting from temperature to pressure. This is an adiabatic pressure equation, and you'll often see this in some formulations of compressible fluid dynamics. Let's get our vectors in here. But this is only true in the adiabatic limit.